Hi, so welcome back. So in this lecture, we will learn about second order linear ordinary differential equation with a sinusoidal input. Okay, so in other words, the external force on the system which gives rise to this second order linear ODE, that force is in the form of a wave, a sinusoidal wave. Okay, so with amplitudes alpha and beta, okay, well, individual amplitudes, a superposition of two waves really, okay. So alpha and beta are constants. Omega is the frequency with which the interference happens in the system. Okay, so as usual, you can always refer to the model on which we built this theory of a body being suspended from a ceiling by a spring, where at any point of time the distance or the displacement of the body from the ceiling is x of xt, okay, x of t. All right, so something from the outside, some force from the outside is disturbing the system, disturbing this body, and that disturbance is in the form of a wave, okay, in regular intervals, in a pattern, which is defined by this. All right, so of course we have to solve it. In other words, we have to find out what is x of t. In other words, physically, we want to find out what will the displacement of the body look like as time goes on. Okay, that is the position x of t. So as always, we want to solve this by the method of undetermined coefficients is the easiest method available. So we need a trial solution. First, we want to solve the particular solution. We want to find out the particular solution. We always know the complementary function, which is the solution of the homogeneous form of this equation. We always know that. We have worked that out. Either it is underdamping, or it's a case of overdamping, or critical damping, or undamped vibrations. Those are the four possible options. So we always know what the complementary function is going to be. But for now, we have to guess. So we want a trial solution. For the particular solution of this differential equation. Okay. So we want to guess what, as a function of time, what can xp be? In other words, what function of t can satisfy this equation? In other words, if you put that function of t in the left hand side, differentiate it twice, differentiate it once, do all of this, it should give out this wave. Okay, so of course the guess here is very easy because we have a sine and cosine, a combination, linear combination of those waves on the right hand side. We think that this should also be a combination of sine and cosine, because after all, if you have a function in terms of sine and cosine, if you differentiate it twice, if you differentiate it once, if you don't differentiate it, doesn't matter. All of this will keep the sines and cosines in terms of sines and cosines. Okay, so sine turns into a minus sine after a double differentiation. Sine turns into a cosine after one time differentiation. So if you have something in terms of sine omega t and cosine omega t, that after all of this calculation should remain in terms of sine and cosine. So that's the guess. So, but of course, we can't have alpha and beta. We don't know what the coefficients of these are going to be. So we're going to take, these are the undetermined coefficients, k and l. We don't know what they are, but we will find that out. So this is my guess for a trial solution, particular solution for this differential equation. So let's try it out. In other words, instead of x, we put this, okay? So we have k sine omega t plus L cosine omega t. This we put in here, so we double differentiate, plus b times, this we put in here again, but we differentiated once only this time, plus L cosine omega t, and then c k sine. I want to rub this out. We all know this model by now. We need some more space. So omega t plus L cosine omega t. This must be equal to, as I said, because this is the trial solution of this, this must give me this. So this must give me this right hand. There's no space here, so this is the right hand side of the given differential equation. So I'm going to say that this, once you put this trial solution in here, it should give you the right hand side, which is the alpha sine omega t plus beta cosine omega t. All right, so let's work this out. Well, differentiating sine and cosine is easy. In fact, we can double differentiate it straight away. So sine will turn after double and these are linear combinations, so you can differentiate them, multiple times without any hassles. So if I differentiate sine 2 times, I will get a minus sine. But this omega will come out twice, so I'll have an omega square. Similarly for this, cosine double differentiated gives me a minus cosine, but with an omega square in front. So let me take that out. Let me take out the square, omega square term. And so this turns into, and both of them produce a minus sign. So I'm going to take out a minus omega square. And this remains what it is, therefore, k sine omega t plus L cosine omega t. I hope that that's easy to understand why this came out, and the rest of it remained the same. For this one, well, if you differentiate both the terms, you will have an omega coming out only once, because the differentiation is only once. So I'll have a b omega. Let's just write that down, because the omega will be common in both of them as a coefficient. But this one turns into cosine omega t, and this one turns into a minus sine omega t. So I'll have a minus L sine omega t. Well, I don't have to do anything with this one. Sine omega t plus L cosine omega t. This must be equal to the right hand side of the given differential equation. So let's just group things here. Can I group the sine, all the sine terms together? So I get a minus omega square k from here. I get a minus omega L, omega b. Yes, there's this L here. Oh, yeah, L. And I get a C and a K plus CK. This will be the coefficient of the sine omega t. What will be the coefficient of the cosine omega t from the left hand side? I'll have a minus omega square L. So I'll have a minus omega square L. I'll have this one, which will be plus omega b k, and I'll have this one, which is a CL cosine omega t, and this will be equal to the right hand side. Okay, so, well, right hand side is alpha, so let's just write that once more. So I have space here, alpha sine omega t plus beta cosine omega t. So we have waves on both sides of the equation, and these are both sine and cosine, so the coefficients will have to be the same. In other words, this coefficient of the sine function will be the same as alpha, and the coefficient of the cosine function must be the same as beta. That's how we find the undetermined coefficients k and L. So let's just write that down. So this is equal to alpha. Well, we can actually group this one a little bit here as well, because k is common between the first and the third term. So let's write C, therefore, C minus omega square k and minus omega b L. This will be equal to alpha, and the other one is omega b k and the L term. So here is, you have L common from these two. So you have a plus C minus omega square L. This must be equal to the coefficient of cosine omega t, which is beta. Alright, let's just solve this. We want to solve for k and L, because those were the undetermined coefficients when we have to solve for k and L. And these are the system of linear equations, and two variables. We can solve that. Well, let's find K first. I want to eliminate L. So I will multiply the first equation by C minus omega square. And I will multiply the second equation by omega b, and I can add the two. That way we have the L cancelling out. So K will be, well, what do I get from the right hand side? If I multiply the first equation by C minus omega square, so I'll get C minus omega square alpha, and I want to multiply the second equation by omega beta, b times beta, and of course something will become the coefficient of K here once we do all of that calculation, and that I can bring down. That way I find K. So what's the coefficient of K here? It's going to be, I'm multiplying the first equation by C minus omega square, the coefficient of L here. So I get a C minus omega square square, and I'm adding, I'm multiplying the second equation by omega b, which is the coefficient of L here. So I'm getting omega square b square. Okay, that's your K. What about L? We do the same trick, except now this time we eliminate K. So I multiply the first equation by, or let's multiply the second equation by C minus omega square first. So I have a C minus omega square. From the right hand side, I'm going to get a beta. And because these are the same sign, I have to subtract. I'm going to subtract the first equation times this coefficient, omega b. So from the right hand side, I will have omega capital B alpha. And then, well, the coefficient, the denominator will remain the same. As you know, this is actually the determinant of the coefficient matrix here. So we all know that. So you can work that out, but it's still going to be the same. Okay, so that's your. I hope that's correct. Okay, yeah. So that's your K and L. So now we have actually determined the two undetermined coefficients, and so it's no more a trial solution. It's actually the particular solution of this given differential equation. Well, it's a little messy because there are too many constant terms here, too many unknown variables here. But, well, actually not unknown. These are given variables. Once the problem is given to you, all these will be known numbers, so you can work out what is K and L exactly. All right. Now, I want to take the case where, let's study the case where this B, if in the given differential equation, B is just 0. In other words, there is no resistance in the system. There is no friction. So the vibration is going to be an undamped vibration. Okay, if in the absence of any external force, the body is going to move up and down all the time. Okay, and there will be no damping in the system. So what happens in that case? Well, in that case, what happens to the K and L? K becomes, well, capital B, this B is 0. The resistance term is 0. So this is 0 and this is 0. And so these two are gone. We have this fraction here, but you have a C minus omega square and you have a C minus omega on top. So one of them will cancel. So this numerator C minus omega square will cancel with one of them here. So you're left with alpha by C minus omega square. And you are, for L, that becomes, again, this B once the B is 0, these two terms are 0, so you're left with the same kind of a problem, except that instead of alpha you have a beta. So your L becomes beta by C minus omega square. So K and L become a lot simpler when the resistance term in the system is 0. When there is undamped vibrations, in the absence of any external force. Okay, right. So, but of course, this is fine. But the trouble comes really when C is equal to omega squared. That's when we can't find K and L. Okay. So all of this is valid. K and L are valid when this determinant from the coefficient matrix, or this denominator here, is not 0. When B is 0, the denominator, well, may not be 0. But if C is equal to omega squared, then we have trouble. Then the denominator is also 0. So that's a case that is worth studying. Okay. All right. We're going to do that. We're going to take the case where B is 0. There is no resistance in the system. And C is also equal to omega squared. What happens in that case? Okay, right. Let's take that up. So I'm just going to leave. All right, I can rub things out. Okay. So in the case, so let's study the case. So we're now doing B is equal to 0. So this is what the differential equation is. All right. No damping in the system. In that case, for xp, the particular solution is going to be k, which was alpha by c minus omega squared. This c is the same as this c. Sine omega t plus L, which was beta by c minus omega square cosine omega t. This is the particular system. Now I make it even more challenging. I say, what if I take the case C is equal to, or omega is root of C? What happens in this case? Okay. In other words, C square, omega squared is C. So the denominator is 0. Well, in that case, what happens to this xp? Well, we are back to the problem that we faced before when we were doing the case of resonance, whether without any external force or with an external force of exponential type. So there were the cases of resonance, and we had the same trouble where the denominator went to 0, and we had to sort of, accomplish or find out what this was. The particular solution was in a roundabout way going through L'Hopital. We're going to do the same thing, okay? So the trouble is when this is equal to 0. So we assume that this is not equal to 0, but it's very close to 0, okay? So we assume that omega approaches root of C, okay? The frequency of the external impact, or external influence is close to, or is approaching this root of C, or something to do with the spring constant. Okay, what happens then? In that case, of course, since this is not equal to 0, but it's close to it, so in that scenario, when this is close but not equal, this is a valid particular solution. So let's just write that down. Alpha by c minus omega square sine omega t plus beta by c minus omega square cosine omega t. However, we know that finally we have to move this to root c. So we just as before, and we've done it many times now, we want to adjust this particular solution by a weight of the homogeneous solutions. Okay, we have that famous result where if we already established a particular solution, we can add or take away a weight of the homogeneous solution, and the whole thing will still remain a particular solution. So we are going to use the same trick, and we've used it before. So let's do that. So in the case of no damping, B is 0, capital B is 0. So what were the homogeneous solutions? One of them was, well, no damping, so no decaying term. So you just have sine some frequency. I've already used omega, so I'm going to use something else. I'm going to use rho t. And the other one, this was one of the solutions. And the other one was cosine rho t, the second homogeneous solution. If there was decay, there would be a minus RT term here, but because there is no damping in the system, you can obviously go back to the lectures where we had covered undamped vibrations. So the two homogeneous solutions are going to look like this. We are going to adjust this particular solution by some weights of these two homogeneous solutions. But of course, the question is, what is this rho? This rho actually came from solving the auxiliary equation for the homogeneous form. The auxiliary equation, the homogeneous form is just 0 on the right hand side. So no influence, no external force on the system. That's the homogeneous system. And the auxiliary equation was just replacing the x by m and the primes by, indices, square plus c, x with no prime, so no square, so m to the power 0, that is 1. This is the auxiliary equation. And the two roots were, what would be the two roots? Plus minus I root of c. Okay, so this is 0 plus minus. So the two roots are 0 plus I root c and 0 minus I root c. If you want to call them m1, m2, just as we have before. But there's no need for now. Okay. And we said that for undamped vibrations, the rho will be the imaginary part of this solution, which is root c. So rho really is going to be root c. Well, just a word of caution for the system that we had in mind for, a body moving up and down or oscillating by a spring. For that, the spring constant, capital C was positive. Okay. So therefore, once taken to the other side, it became a negative C, so you have the I coming out. So that's why, you have the root I. Okay, anyway, so these are the two, we had covered all of that in the lecture where we did undamped vibrations. So we want to adjust this by some weights of these two equations. So let's do that. I want to take away some weight of this. What weight? The same as this. Okay, I want to take away alpha by c minus omega square weight of sine root ct. And I want to take away, I'm just rubbing this out because we have established what rho was. I'm taking away beta times, or beta by c minus omega square. Same weight as this cosine root c t. So let's just group that. So what do I have? I have if I want to, so you have a denominator of c minus omega square throughout. So here I have alpha. If I want to group these two, I have alpha and then sine omega t minus sine root c t. And then from these two, I have beta cosine omega t minus cosine root c t. Okay, and the whole thing is divided by capital C minus omega squared. That's the adjustment. But of course, we said that we have to finally make this equal to approach the root c. So we are basically taking limits. We are always taking limits because we are working in the area where, or with the condition that omega is approaching root c. Okay, so therefore this is going to be limit. So limit of the whole thing here, omega approaches root c. Well, with that adjustment, I'm back to the 0 by 0 form of L'Hopital because you see when omega approaches c, root c, of course, it means that omega squared approaches c and this denominator is 0. But as omega approaches root c, this frequency here becomes root c, which is the same as this, so this will vanish. Similarly for this, root c and root c, that will vanish. So we're back to the 0 by 0 form of L'Hopital. And let's just do that. Well, what do? We differentiate with respect to omega, because omega is the variable, and that's the one which is approaching this constant root c. So I take limit omega goes to root c, and I first differentiate the numerator with respect to omega. So alpha is a constant. This becomes cosine omega t, but now here t is the constant because omega is the variable, so t will come out. What about this one? Well, the whole thing here is a constant with respect to omega because there is no omega term. T is not the variable here. That's important to remember. So I get a 0 from here. What about this? Well, again, this one has no omega term, so that plainly just gives me 0. Here, I'll get beta is the constant, and this will give me a minus sine omega t, but again the t will come out because t is the constant. And what happens to this one is that you get a minus, if you differentiate this with respect to omega, you get a minus 2 omega. Alright, what form is it now? Well, I can now write omega equals root c, and because root c is not 0, c is related to the spring constant. It's the spring constant k by m, which are non-zero. So I have a non-zero term in the denominator. So it's not in the 0 by 0 form. We're out of danger, and we can freely put omega is equal to root c. So let's take the negative sign out and change the positions of these two. So basically I have beta t sine root c t, because omega now turns into root c because we're making them equal, and this gets a negative sign because we're getting rid of this negative sign. So I get alpha t cosine root c t, and the whole thing is divided by 2 root c. Okay, that's the solution. That's the particular solution when we have two conditions. One is there is no damping, b is equal to 0, and when the external interference has a frequency matched with the spring constant, okay, which is represented by the c, capital C. Okay. So if these are the two solutions for undamped vibrations, in other words, when in the absence of any external force, in other words, the right hand side is 0, that was the homogeneous form of this equation. So what's the complementary function? The complementary function will be a linear combination of these two. So I'm just going to write it out here. The complementary function xht for homogeneous, when in the absence of an external force, it's going to be a linear combination of, let's say, C1. Don't confuse C1 with this C. C1 is just another constant. Sine root Ct and a C2 cosine root Ct. That's the homogeneous solution of the system. In other words, without the in the absence of the external force. So the general solution. So if I want to write down the general solution in this condition, the general solution given this condition is going to be xt, which is the final solution, is going to be the particular solution plus the homogeneous solution. And what is that? Well, it's just the particular solution is this plus this. Okay? You have sine and cosine terms here. can I just group them and write them together in a nice way? So if I group this one, so this is your xp, by the way, and this is your xh. So if I want to group the sine root c term, what I get from here is, from the xp, I get a, or let's write it this one first. So I get a c1 plus beta by 2 root c t sine root c t. And from these two, I get c2 minus alpha by 2 root c t cosine root c t. Well, what does this solution, this is the solution of the differential equation in the case of an undamped system, but with an external force in the form of a wave like this. What does the system signify? Well, again, we're back to the case of resonance, really, because even though these two are just simple, oscillations, they don't go beyond +1 and -1. It means these two terms suggest that the body, which is really hanging, okay, this body hanging from the ceiling by a spring, these two terms would suggest that it would move up and down. But the amplitude here, the two amplitudes are polynomials, okay? It's a polynomial of degree 1, so it's a line. So it's a growing function. So the amplitude is growing. Well, this is growing. We don't know actually whether it's growing or decreasing, because that depends on what alpha and beta are, okay? If, for example, alpha is negative, so then in that case, this would be a growing function, because negative alpha and this negative will give a positive t here. And beta is positive, okay? Whatever, depends on the combination. Let's say the combinations are such that these are growing. In that case, we have a resonance. You give it the initial pull and you let it go, but in the presence of this external influence. And so the body, whatever the vibration is it starts with, it grows with time and it sort of goes on. And here there is no stopping it. This really is closer to the Tacoma Bridge collapse model, where even though the bridge, had its own natural oscillations, but it really started oscillating in the presence of an external wind. So the wind sort of hit the bridge in a wave fashion, which matched with the constants of the bridge, the spring constants. It is like a spring, it will move up and down. So once the external influence of the wind wave sort of matched with the constants of the internal system of the bridge, it just took off and it went on and on and on and without any stopping, and so finally it had to collapse. Of course, if alpha and beta are such that this becomes a decreasing amplitude, these two, in that case the body would move but with a decreasing oscillation, and so it will finally stop. Okay, so it all depends on what this external influence is. It can give rise to a resonance, in fact, an uncontrolled resonance in this case, where there's nothing stopping. It goes on because the amplitude will keep on increasing as you increase time, if the alpha and beta are right for that. Or in the other case, when alpha and beta sort of adjust themselves in the way that the amplitudes are decreasing, in that case, the system is probably safe. Okay, so, well, I think we will finish it here. We've not only done this differential equation with the sinusoidal input, we have also covered the case where there could be a possible resonance when there is no damping in the system. Okay, and the external influence sort of matches with the constants of the internal system. All right, I think we will finish it here, take things forward in the next lecture. Thank you.